I think it's time for we to start. And welcome everybody to today's CITA seminar. And we're very happy to have Jose Maria Ezquiaga visiting us from Chicago. I hope I did that right. Yeah. Jose is currently an Einstein Fellow at the Copley Institute for Cosmological Physics at University of Chicago. And he got his PhD degree from Madrid in 2019. And his research focused on probing the standard cosmological models with the gravitational waves, exploiting both the LIGO and the LISA data. Yeah. And we're very happy, Jose, to give us this virtual visit. And now I will let's welcome Jose, and I will give the microphone to you. And please go ahead, Jose.
Thanks a lot. Okay, so you should be seeing full screen now. I'm really happy also to be visiting CITA virtually and sharing with you the science that I've been working on recently. I'm very happy that people ask questions during the talk, so please do not hesitate to stop me at any point. I think it's more fun if this is more like a dialogue. The topic of today is essentially what we can do with gravitational waves to learn about cosmology, the laws of gravity at large scales, and all related to that. But I think before getting into the details, it's nice to set up the stage and understand where we are now. So now there's been already 3 observing runs of the LIGO and Virgo collaboration, in which we have detected about 100 events, which includes binary black holes, binary neutron stars, and recently in the last one, binary neutron star black hole binaries. So these black holes span through different masses. This plot encompasses on the vertical axis their masses, and it highlights when the origin of these black holes compared to comparing gravitational waves in blue to electromagnetic black holes in red. So with all these 100 events, there is a ton of astrophysics that can be done. To us, black holes will be just a tool, binary neutron stars, to learn about the cosmos, but of course there are so many other things that can be done with them. But despite we are all very excited of these 100 events, it's important also to remember that this is just the beginning. And to exemplify that, I like to show these plots where in the left you are seeing the number of detections as a function of year. So this is until now, the 3rd observing run, we have about 100 events. And then on the right, you see the horizon redshift. So this means how far our detectors can see as a function of the total mass. So you see that at most, our detectors could see sources now below redshift 1, although typically most of them are like below redshift of 0.6, more or less that. Now, this is going to change soon as we move to the next upgrades of current technology. So within the same technology that we have today, what is known as 2nd generation detectors, there is planned 2 more observing runs, one starting in about a year, which will be 04, and then later 05, which will have like the final design sensitivity of LIGO and Virgo and Cagra. So you see that in the next observing run, we will be getting hundreds of events. So essentially kind of like 1 event per day. And then these events will be starting to go further in redshift, getting to events beyond redshift of 1. Now, the biggest change will happen with what is known as the 3rd generation of gravitational wave detectors. That will happen more or less in the next decade, 2030 something. Is not yet clear, but here you see that we will get, I'm focusing now in particular on the green line on the plot, we will get hundreds of thousands of events per year, if not millions. And we will essentially detect these black holes and compact binaries throughout the history of the universe. So you see that if you, for example, think of a total mass of 100, on the right, you see that you can essentially cover all the history of the universe where stars have form, etc., etc. Here in this plot, there is also LISA, which is the future detector from space, which, because it's at lower frequencies, will detect gravitational waves of binaries which are much more heavy. So this is more, LISA is more for supermassive black holes and intermediate mass black holes if they are out there. Okay, so we will get a lot of events, and each of these events also will come with higher sensitivities, better polarization measurement, and localization. So this will allow also to do a lot of improvements in terms of testing, for example, the theory of gravity, to look for deviations in the waveform, etc., etc. But for us, for today, the fact that we will have many events at high redshift will be the key. Now, so when we think in simple terms of what happens when a gravitational wave, when a compact binary merge, then it perturbs the space-time around them. It produces a gravitational wave, which is going to travel across the universe. So as these gravitational waves travel across the universe, it will essentially get a stretch because of the redshift, and it will also decrease its amplitude because this is a spherical wave, and you are detecting the amplitude, so it scales as 1 over the distance. So when we when we in our detectors detect a signal, the two quantities that we have direct access to are in fact the luminosity distance and the redshifted masses. So we detect quantities in the detector frame. Now, if you want to do cosmology, from here, you can guess that the simplest way is to focus on the luminosity distance, because the luminosity distance already encodes directly the Hubble parameter that determines the rate of expansion. Now, the key question with gravitational waves is how you get the redshift, because the redshift doesn't come directly with the signal. So the most direct way of doing cosmology with gravitational waves is focusing on the luminosity distance, but in those events in which we observe a counterpart. And why is that? Because if you observe the counterpart, from the counterpart you can get information about the redshift, and then your problem is solved. Essentially, you have from gravitational waves a direct measurement of the luminosity distance, from the counterpart a direct measurement of the redshift. You can draw your Hubble diagram and constrain cosmology. And this was the case of 17017, the binary neutron star binary that we all love, that happened in August of 2017. That in that case, this was a very nearby event, 40 megaparsecs. So we only had information about the Hubble parameter, the Hubble constant, sorry. But if we were to have events at higher redshift, you can start to constrain other parameters. Now, for this method, of course, the key is that you need to have counterparts, and in order to have counterparts, you need to have some matter around the binary. So if you have two black holes in vacuum, you are not going to generate a counterpart. Typically, you need a neutron star to be involved. Now, we know now that, at least at the moment, our sensitivity to neutron stars is lower, just because the volume that we can access them is smaller. So moving forward, I guess one of the big questions of this bright-sided method is how many counterparts will we get, and if we will be able to detect them at high redshift. So I'm thinking of now next generation detectors. I saw you that you will go, we will go to redshift much larger than 1. Can we detect direct counterparts and identify them at those redshift? That's a question that needs to be addressed. But without focusing on a concrete counterpart, you can also do cosmology in a statistical way. If you say, okay, I know my gravitational wave is coming from this region of the sky, because we have different detectors with different orientations, you can triangulate where the signal comes from. We don't have a great angular resolution, but we have something. And then you can ask, okay, I know this region of the sky. I know my error in the luminosity distance. This means a volume. So if I have a galaxy catalog, I can say that my gravitational wave has to come from one of these galaxies in the error box that I have measured. And then you can statistically infer the cosmological parameters. So this method works well. And this, by the way, has been applied several times to real data. one of the first examples was 170814, which is what is shown in the plot. Anyway, for this method to work, you can imagine that one of the keys is that your error volume is small, because if you have an error localization in the sky of like tens of hundreds of square degrees, then like your number of galaxies in this volume will be huge. So you need to have localizations close to a few square degrees. Moreover, you need to be sure that your catalog is complete, because otherwise you are introducing a bias while you're doing this analysis. So from this perspective, dark sirens are a promising method because you don't rely on direct counterparts, but it also has its complications because you need to have complete galaxy catalogs at to high redshifts. Now, if we forget for a second about measuring cosmology, and we fix our cosmological model, then this is what the LIGO and Virgo collaboration do all the time when they are doing astrophysics. So for astrophysics, they fix the cosmology to be Planck, and then from the luminosity distance and the redshifted masses, if you know the cosmology and you fix your theory of gravity, you can directly connect to the redshift, and you can also directly obtain the the source masses. And with this, you can do constraints, for example, on the merger rate as a function of redshift, and also the mass distribution of your compact binary population. But this analysis assumes a given cosmology. So the method that I will focus on for the rest of the talk is a combination of these last two. So essentially, we will be doing astrophysics. We will be inferring the mass distribution of our population at the same time that we are doing cosmology. And the key for this method to work is that, as I said at the beginning, we are measuring redshifted masses. So if we were to know a reference scale in our mass distribution, then by looking at how this reference mass scale changes as a function of luminosity distance, then we can invert this equation that is highlighted in green. If you know m and you are measuring m set at different luminosity distance beam, then you can obtain the redshift. But for this method to work, to work in practice, you need to have some kind of feature in your mass distribution that you could identify. And I'm thinking here, for example, if you have suddenly a gap in your mass distribution, suddenly your rate drops, or you have a break, all of these features are easy to identify in a data analysis perspective and allows you to do this method. In principle, given for next generation detectors, this method could be done in a totally non-parametric way, because at the end you will be measuring your mass distribution at a low redshift, and then you will see if this mass distribution is the same at different redshifts. But this is, maybe we can discuss about this later. So for the first part, or most of the talk, I will be thinking about doing cosmology within the realm of lambda CDM, and in particular, I will be thinking of how well you can constrain the cosmological parameters like H0, omega matter, etc. But in general, you can do more than that, and at the end of the talk, I will also mention how you can change, how you can study, for example, the validity of gravity at large scales. So I'm gonna start talking about what we have observed so far. So I don't know if there is any general question about the method and this introduction. Okay, if not, I will continue, but please don't hesitate to stop me at any time. Okay, so what have we observed? So I said there has been 3 observing runs. The latest catalog that encompasses all of our observation is what is known as GWT-TC3. Right, so in this plot in the bottom, which I know it's very busy. What is being shown is the merger rate distribution as a function of the primary mass. Okay, and here in this plot, what you are seeing is the outcome of different models that the LIGO and Virgo collaboration has done. So, for example, this Binet green line corresponds to a Bin Gaussian process, which essentially gives to you have as free parameters the height of your bins in the mass at different mass ranges, and then you feed from the data doing Bayesian inference the height of these bins, asking that there is some continuity more or less between different bins. These flexible mixtures is also a kind of non-parametric model, but there are also here in this plot you see more parameterized models such as a power law plus a peak, which is the pink line. Anyway, I don't want to enter into the details of the different models, but I think what we are seeing from here, there are a few.
Could I just ask about, I mean, this is actually technically interesting how you're actually trying to do the fit. What's power law plus peak? It means you're putting in a power law and then you're adding the possibility of a peak that's floating in location and width.
Exactly. Yeah. So you have
and the power law plus spline, is the spline representing deviations from the power law that's over any part of the M1 spectrum?
Exactly.
Okay, good. And flexible mixtures is what?
Yeah, flexible mixtures, I haven't worked with it myself. I think it's a version of kind of like this Gaussian process, but for more parameters.
Yeah, right. So it's a bunch of templates that are fit to the data with parameters, presumably. Okay, sorry to have interrupted. It's just that
no.
From a technical point of view, everybody is always trying to fit distributions, and this is interesting to know the methodology.
Yeah, no, absolutely, and I think it's important for the discussion that follows. So thanks for asking. It's a good point. I think the only thing though is that I think at least as I try to understand these plots, I try to do it more broadly, more than like the specific features. I mean, some of the small features that you see, because for example, you see in the power law plus spline model, the blue line, you see there is a lot of like wiggles around here. I think it's still under investigation, and we are doing some work here at U Chicago, whether some of these are just like, I mean, I don't know, a statistical fluctuation, or there is some astrophysics there. So I think overall, to me, like the features that are clear is that there is something happening like around here, around like 40 solar masses. There is something that we are clearly seeing that we cannot fit, for example, our whole mass distribution with a single power law. So there is something that is making the rate of binary black holes to drop below this value. And I remind you here that the vertical axis is in a log scale. So there is a substantial break around this mass. There is also the point that here we might start to be seeing like kind of like a maximum at around 10 solar masses or so. But this is also something which is a bit more complicated to analyze when you are doing only binary black holes in your analysis, and I will comment about this in a second. And then the last point also here is that if we are seeing this decrease in the merger rate for higher masses, and then we might ask if there is like actually a gap about the in this mass range, and this is interesting because like the theory of peristability supernova, which has this as a prediction, because in this in our understanding of how black holes form in the field, if they form from a star and the star is getting more and more massive, there is a point in which in the core you have enough temperature to produce electrons and positrons that generate a runaway process that essentially like ejects enough material so that you cannot form these heavy black holes. So we are not seeing quite the like an empty gap, so to say, because we have some events here around 60 solar masses. But at least this drop in the rate seems to be consistent with that theory, which might mean also that this catalog of event has binary black holes from different populations. Anyway, going back to the point of the maximum mass, for that, I think what you need to understand and analyze is the full mass distribution at low masses. So this is what the plot in the top right is doing. And here also, so the Bean Gaussian process is the same as before. The multi-source, I believe it's doing is parameterizing the binary black holes, the neutron stars, and the neutron star black holes, each of them with a parameterized model, but that can be with different, different weights for each of them. And then there is the power law plus deep plus break model, which is essentially a model in which you have power loss at low mass, for the binary neutron stars, like below 3 solar masses, and also for black holes, but then at large masses, but you allow the possibility to have a gap in your distribution. So from here, oops, sorry. From here, the relevant features that we see is that there is a clear drop in the rate of binary black hole, of compact binaries around 2.5 solar masses. So this is sort to say is telling us that binary neutron stars have a rate which is much larger than the one of black holes. The other thing that comes from this analysis is that you cannot fit also all the neutron stars and the black holes with a single power law. So there must be something happening. Then the question of whether there is a gap between the neutron stars and the black holes, data cannot tell us yet. And this is because for these low masses, we still have just not that many events. So at the moment, let me go back for a second. At the moment, the part where we are more sensitive to of our mass distribution is precisely this high mass range. So above 50 to 60, about 50 solar masses. This is the part where our detectors are more sensitive. So this is why this break that I was mentioning around 40 is statistically very robust. So so this is a feature that we are seeing in our data that people have used to do cosmology. Now, if there is this feature, and we assume that this comes from the theory of peristability supernovas I was explaining, this is telling us that there should be a gap, but at some point there should be black holes that start to form again at higher masses, because when you have even higher masses in the stars, other processes are relevant in the formation of the black holes. So this population of black holes, which is would be above the peristability supernova gap, has not been detected yet, but it could potentially be detected in the future, and this is what we, Dan Holth and myself, call the far side binaries. So something just to mention about these binaries, which is interesting, is that if they exist, they will be like perfect sources for multiband astronomy. So for multiband astronomy, what I mean is detecting the same source first with LISA from space, because with space gravitational wave detectors, you get like lower frequencies, so you will be seeing the spiral of the binary, and then a few months or years later, you would see the merger of the signal with your gravitational wave detectors. So this plot shows the fraction of multiband events as a function of the total mass. And if you are thinking about these far side binaries that could be above the peristability supernova gap, this is something like about 200 or 300 total solar masses. And you see that the fraction of multiband event is significantly larger for the population of black holes that we are seeing so far, which is essentially below 100 solar masses in total. Now, this was a bit of an aside, but just to motivate also this far side population. So one of the things that I want to address now is, okay, if we consider this full population of compact binaries, what can we do with all of them for cosmology? And for this exercise, I was arguing that there are still like many uncertainties in our data, but let's make a few hypotheses. And what we are gonna assume is that in fact this peri-instability supernova gap exists at above 50 solar masses. It is not. We are not gonna take a sharp gap, sharp edge at around 50 just because we know already that there are some events at 60 solar masses, but let's assume that there is a break in our power law distribution, and then above the gap there could be a potential far side population. And then at low masses, what we are going to assume is that there is a neutron star black hole gap. So our population of black holes will drop, and then we have the binary neutron stars at lower masses. We are, for the analysis, I'm going to take this like very toy model, like uniform and broken power law distribution, but at the end, that is something which will not be that relevant, because what you care mostly is the fact that there is these features like gaps for your analysis. Also note that if there was to be any other feature like a peak, for example, in the power law plus peak model, this will only add additional information that you can get from the mass distribution. So this will be like the toy model population that I will be using. And then what the bottom panel is showing is how—
Could I just ask another question on this? I have a particular interest on the far side. Is that a projection that there will be the ability to do greater than 120 solar masses black holes?
Yeah, so that's
the problem in the past is that the frequencies were out of the LIGO range, and so it's because things have been extended or the noise has been decreased that one's been able to go into that regime?
Yeah, that's an excellent question. So first, as I said, like the fact that this population might exist is a prediction of the theory of peri-instability supernova gap, but we have not detected. So the rate that I'm assuming here comes from the upper bounds that we have. So we can so we are not super sensitive at, let's say, 20-30 hertz. So at low frequencies, our sensitivity stops. Our sensitivity falls because seismic noise, and then it becomes more difficult to detect gravitational waves. But still, we understand more or less our noise, so we can put some upper bounds there. The problem, mostly, I think, for these high mass events, is that they become so short in time that then there could be glitches which last for the same amount of time as the gravitational wave signal itself. So essentially, instead of seeing like all the spiral, all the oscillations, and then you see the chirp, where for these high masses you only see like one or two or less than 2 cycles, and then it measures. So it's very difficult for that. I mean, it's more difficult that to deal with glitches when you have like that masses. There is the expectations that as we move to design sensitivity, there will be a bit of improvement on that low frequencies. And then moving forward to third generation detectors, there will be a planned improvement at low frequencies as well. So that will be much more significant.
But there must be a constraint on, even in spite of the fact that in terms of overall gravity wave luminosity, these would be really impressive events. There's presumably you know, a pretty stringent redshift that you can see them to because of the redshift effect on the gravity wave signal.
Yes. So, right. Sorry, I'm not sure if I'm getting right the question. So we can place constraints from the fact that we have not observed them. I mean, we know our sensitivity at these frequencies, and we know how far we can see these detectors, these events. So that allow us to put a overall constraint on the rate. Is that your question, or is something else? Sorry.
Well, no, it's, you know, once upon a time, I used to say that there is the ring of fire way out there where there's a large number of very massive objects, some fraction of which will form holes. But the trouble is the redshift would be high enough that you aren't just dealing with those that are nearby, the frequency of that signal. It's being pushed out to longer frequencies, or, you know, lower frequencies.
Right. Yeah. Okay. Yeah. So yeah. So I assume, yeah, that's I mean, so here for these plots, I'm assuming that these binaries has a merger rate evolution that follows the star formation rate. So essentially, you have something which increases from redshift 0 to around 1.5 and then decreases. So that determines, so this merger rate evolution determines the number of events at different redshifts. And then given our sensitivity, you can see some of them or not. So for example, in the lower panel, what I'm showing is the same toy model population that as in the upper panel, but then I'm plotting how you see the mass distribution at different redshift bins. So, and also I'm doing it for different detectors. So the dashed lines corresponds to current technology, what I call second generation detectors, and the solid lines corresponds to next generation detectors, 3G. So you see, for example, that when you are with two generation detectors, you are really constrained by your horizon redshift to detect this binary. So in particular, for example, at low masses, you see that you only detect binary neutron stars which are below redshift of 0.5. For the more massive events, essentially at high redshift, let's say, for example, like beyond the extreme case, beyond redshift of 2, you are only detecting the most massive events. So for each mass range, you have a different horizon. So this means that if your population, for example, if your black holes were merging, like I don't know, at very high redshift, but and we are beyond our sensitivity, of course, those we will not be detecting. So I see there is a question in the chat. Okay, but it's okay. Great. Please come back later if there are more questions related to that. Okay, and this also to go further on the topic of the redshift range. Here, this is the detected distribution of compact binaries as a function of redshift for different mass ranges. So you see on the top left, this is binary neutron stars. On the top right, this is binary black holes below 7 solar masses. On the bottom left, binary black holes above 45 solar masses. And on the bottom right, far side binaries. So you see, for example, something which is very interesting, which is how even now, I mean, how now for when we are thinking of binary neutron stars, we are only seeing them very locally, but their intrinsic rate is in fact much larger. So when we will move from from second generation detectors to 3G detectors, then we will our number of detections will be dominated by binary neutron stars, and you can see this by comparing the solid line in all the different panels. So you see that you can see that the total rate is much larger for binary neutron stars. So what this means is that when we are trying to do cosmology with the full mass distribution, this will the parts of the mass distribution that will be relevant for us will change. So here, this plot shows the estimate on the constraints on the Hubble parameter as a function of redshift. On the left for second generation detectors, on the right for third generation detectors. And this each of the lines shows the projected constraints using each of the features of the mass distribution. So the fact that you have a minimum neutron star mass, or the fact that you have a neutron star black hole gap, each of the edges give you a reference scale that you can use for cosmology, and the same for the peri-instability supernova gap. So you see that on the left, the one that is given best constraint is the lower peri-instability supernova gap. And this is giving constraints which are better than 10% as redshifts below 1. You see also, again, as we were seeing in the previous plot, that you cannot get binary neutron stars beyond redshift of 0.5. So this is why you only have one dot on the binary neutron star lines. However, this changed completely for third generation detectors, where in fact our inference of cosmology will be mostly dominated by the neutron star black hole gap. And you see that the orange line, the lower edge of the binary neutron star black hole gap, will be the dominant one. And when we are thinking of black holes, the most relevant one will be the minimum black hole mass, so to say, so the green line. So so this is to emphasize that like now people is focusing a lot on this peri-instability supernova gap, but what will be most important for the future is the neutron star black hole gap if it exists. So of course, when we are thinking of doing cosmology with this method, there is like the key question of, okay, you are inferring your redshift from features in the mass distribution, and you are looking how these features change as a function of luminosity distance. What if the masses of your mass distribution also change with redshift, which is something that is reasonable to assume because we know that metallicity changes across cosmic time. So what happens with your mass distribution? So what I want to argue is that even if the mass distribution changes with redshift, we will be able to break these degeneracies. And a simple way to understand this is in this plot that I'm showing here. So the top panel corresponds to the detected distribution of redshifted masses. So here, this is different from the previous plots in which I'm plotting masses in detector frames. So directly the quantity that we infer, that we measure with our detectors. And here we have on the thick blue line corresponds to the detected distribution at low redshifts. I mean, near redshift 0. And then the solid lines, the solid thin lines corresponds to a higher, another luminosity distance being at higher redshift. And then I'm changing, for example, H0, and I plot the results of doing that. So you see that essentially when you are redshifting your mass distribution in the detector frame, because this is in log scale, this is just shifting the entire distribution. So you shift the entire distribution, and then the rate of this displacement is what is telling you the rate of expansion. So if you change H0, then you will move moving farther or slower. Now you can compare this, for example, with the case of in which this break point in the power law at around 50 solar masses. If this break point, for example, shifts with redshift, then what will happen is that you will have something like the panel in the bottom. So you will have that this breakpoint can either increase if we have this gamma parameter being positive, or decrease if you have this gamma parameter to be negative. Now, what is important is that at the local level, of course, this if we are focusing only on the region near this break, this is degenerate with cosmology. But then when you are looking at the full mass distribution, and in particular when you are using different features, then for this to be degenerate, you need all the features to evolve in the same way that is degenerate with cosmology. So if you look at the mass distribution, what you are actually doing for this analysis of cosmology is you are seeing if the shape of the full distribution changes or not. Moreover, when you focus on the redshift evolution, you can also rapidly realize that the redshift evolution it might be very different from what cosmology is telling us. So in particular, if you are in the context of lambda CDM, you know the functional form of your Hubble parameter. So this plot, for example, is showing on the top. This is the Hubble parameter as a function of redshift, and then the shaded regions, the shaded bands corresponds to changing H naught by 0.1 or changing omega matter by 0.1. So if you are changing H naught, you are just rescaling your Hubble parameter. If you are changing omega matter, then this becomes you are affecting more at high redshifts. Now, if you compare this to the Hubble parameter that you would infer if there was an evolution of your mass distribution and you didn't know it, then the dashed lines is the result of that. So this is assuming that you are doing this method of tracking a feature in your mass distribution, but you don't know, you didn't realize that this feature is also moving because of an astrophysical process of an evolution of your mass distribution with redshift. So for this simple toy model, linear model, what you see is that the effects of the evolution are different than what cosmology is doing, and this is more obvious when you look at the bottom panel, which is the residual. So just taking the difference with the fiducial cosmology. So to show this more quantitatively, this is the result of doing a Bayesian hierarchical analysis with a mock population of 10,000 binary black holes using the sensitivity of 3G detectors, so next generation detectors. And this is the results for the in the plane of H naught omega matter. So here, this is the result of doing the analysis without parameterizing any evolution in the mass distribution, but in which the mock population, so the simulation, the simulated universe that we are doing, might have some evolution. So in particular, so each of the posteriors that I'm showing here corresponds to a different simulated universe. So in the blue line, in the blue contours, this is the result of doing of having a simulated universe in which there is no evolution. So in this case, if you do the analysis without including the evolution, you don't really care because that was not in the model, and then you recover your injected values, which in this case were like Planck cosmology. So you see that the blue contours recover the fiducial cosmology. Now the green line, the green contours corresponds to the case in which the simulated universe is changing the maximum mass of your black holes. So it's shifting only one of the edges. And then what you see is very interesting because it's shifting a little bit, but essentially the central values are still consistent. And this is because with third generation detectors, as I've been emphasizing, we will be more sensitive to low masses. So what you really care is that the minimum mass is fixed. Sorry, what you really care is that you understand the minimum mass. So in this model, because there is no evolution of the minimum mass, then you recover the cosmology properly. However, in the last example, the red contours, when you are changing both the minimum mass and the maximum mass, you can really bias your cosmology. So what this is telling us at the end is that yes, cosmology can be biased if you don't include the evolution. What is important, though, is that when you do include the evolution, you in fact can recover both the cosmology and this evolution of the mass distribution. So with third generation detectors, we can break this degeneracies, and this is because we have a lot of events across all the mass ranges and also across different redshifts. So we are able to see these two distinctions that I was making, both in the change in the shape and also in the merger rate. And at the end, what you see is that when you are looking at 3G inference with these 10,000 events, which roughly corresponds to 1 month of detections, you can get sub% precision constraints on the expansion rate at redshifts beyond 2, which is pretty interesting because when you see, for example, projections of what DESI would do, this is the panel on the right, then you see that in principle, this simple forecast is better than of what DESI will be able to do. Now, when you think of our current detectors, then this same issue happens. The thing is, like with current detectors, we are only seeing much closer events, so we cannot constrain really well omega matter. So omega matter, this is the same plot as before, but for 1,000 events, which more or less is like 1 year of detections at the same sensitivity. You see that omega matter cannot be constrained. You still have this bias if you don't include it if you don't include the evolution. But if you include the evolution, you can also break these degeneracies, and what you get is more or less like less than 10% constraints of the expansion rate within 1 year of observation at redshift below 1. So still something which is relatively interesting. So for the last 2 minutes, I'm gonna just say that this discussion that I was framing for constraining the expansion rate can also be enlarged to test in general if the theory of gravity is correct. And that is because in general relativity, there is this concrete predictions that the luminosity distance of gravitational waves has to be equal to the luminosity distance of electromagnetic radiation. So if you see any deviation from this will be a smoking gun of physics beyond general relativity. And in fact, if you are thinking of dark energy models in which you have a scalar field that couples to the graviton, it is possible that you modify the propagation of gravitational waves and you introduce sort to say like an additional friction term that is going to change the amplitude of your gravitational waves. So it's going to change your luminosity distance. So you can follow the same. So this you can constrain if you have like a counterpart as it was done with 170817. But what is more interesting, because this modification of the luminosity distance will be accumulate over long distances, is more interesting if you can access higher redshifts. So that is why doing the analysis with binary black holes using the method of the mass distribution that I've been describing, it's a bit more powerful. And this is what we find. So if you are changing your theory of gravity, you are essentially changing how far you can detect your black hole. So because if you are amplifying the gravitational waves, it's obvious that you will be able to see farther away. And if you are decreasing the amplitude of the gravitational wave, you will only be seeing like the closer events. So all your inference of where the inference of where these mass scales are, these reference scales like the peri-instability supernova gap locates, depends also on our assumption about the theory of gravity. So in the standard assumptions that the LIGO Virgo collaboration do, there is, I was saying, you do like Planck cosmology, but if you are changing, for example, the theory of gravity, then this peri-instability supernova gap edge could be at higher or at lower masses. And at the end, what you see is that doing again a Bayesian inference, you can constrain this you can constrain this CM parameter, which parameterizes your modifications for gravity to a level which is about an order of magnitude better than what you can do with 17 over 17. So there is a lot of improvement just because of using black holes which are at higher redshift. But anyway, just to conclude, we can do cosmology only with gravitational waves if we are analyzing their mass distribution and cosmology at the same time. And if now we are interested at higher masses around the pair instability supernova gap, but in the future, low masses will be the most relevant for doing cosmology. And by analyzing the full mass distribution, we can break some of the degeneracies between astrophysics and cosmology. And we hope to achieve this amazing number of sub-percent precision constraints on H of C with 3G detectors. So that's all. Thanks a lot.
Oh, great. Thanks, Jose, for this wonderful talk. Let's first give Jose a virtual applause.
Thank you.
Now let me open the floor, see if anybody has any questions. Please just unmute yourself and speak out. Yeah.
Hi.
Hello.
Great talk. Thank you for a great summary of your work on this stuff. Something that maybe you have touched upon briefly but hasn't been shown in the figures is how this mass gap method to extract H0 from gravitational waves, how does it compare to, say, the statistical counterpart method, which is used now by the LIGO collaboration?
Yeah, that's a great question, and I didn't show results for that. So how the LIGO collaboration do it now is that when they are doing the statistical method, they fix the mass distribution. So it has been shown, and this is part of in the latest paper, that if you allow this mass distribution to evolve, of course, sorry, if you allow your mass distribution, if you don't fix it, you also fit it with the data, then your constraints loosen a bit. So if you are fixing your mass distribution with a statistical method nowadays, you can do better. If you don't fix it, then you do worse. But I think what is more interesting to me is the fact that moving ahead, I mean, I don't know, but like, will we be able to have like complete galaxy catalogs at Redshift 1? I guess that's one of the things that I think is important moving forward for doing this comparison between the two.
And finally, maybe this is a question about the very far future, but so technically also the redshift distribution will have a feature, right? And ideally, the best constraint will come from combining all of this, like the mass and redshift distribution and the clustering, let's say, with a counterpart finding. Are there any ideas of how complementary these methods are? Which one is better? Like you've been focusing on the mass.
You mean the fact that we will detect the peak?
Yeah, exactly. Which would be like redshift 2, so God knows when, but.
Yeah, exactly. So I think, so it is indeed more constraining what you can do with the mass distribution than with the redshift distribution. But it's true that this will add some information, and there are and you can do complementary approaches. So, for example, there is this idea that with binary neutron stars, we might be able to know very well the merger rate, the merger rate history by the time that we have third generation detectors. So if you know the merger rate history, then again, you can, as you said, there is a feature, and identifying that feature helps you constraining cosmology. But this is only if you know the merger rate history a priori. If you don't, then I think you have to fit everything at the same time, and it's more powerful, at least according to my results, using the mass distribution.
Perfect. Thank you.
Thank you for the questions.
Yeah, okay, so any other questions from the audience? So, okay, if not, I think we are almost running out of time. So let's give thanks, Jose, again. And
Thank you.
Jose has also a few available time slots for the individual chat. And if you're interested in talking with Jose, please sign up in this Google Sheet. Yeah.
Yeah, also, there are only a few. So if people, this time doesn't work, don't hesitate to shoot me an email and we can maybe find another time. That's also fine.
Okay, yeah, thank you, everybody. Thanks, Jose. Yeah, let's stop here.
Thank you.